video 831, and the goal here is to be able to see how to perform operations with matrices, addition, subtraction, multiplication, and so on. So the first thing that we want to know is how we talk about matrices. We will either use a capital letter, A, B, or C, or more, depending on how many we need to talk about. Or we may use a lowercase letter enclosed in brackets such that shown below, that can denote a matrix. So notice this is A, and it says I, J. And the IJ are important because they're actually going to be the order. It'll be describe an element, one element of our unit. So that I is the row number, and J is the column. So the element Aij is in row I and column J. And like they describe here, A32 is in row 3 and column 2. So we don't want to think of that as 32, it's 3, 2. So this is, for instance, to describe all the different corners and spots of this matrix. These are the different ways we talk about it with the subscript. The next thing that you need to know is the word order. When we talk about the order of a matrix, it's really its dimensions. Okay, so an M by N order means, once again, rows come first. Means we have M rows and N columns. Okay, so these are your just kind of the basic logistics that you're going to see throughout the rest of this chapter. So this is a simple, very simple logical fact. If two matrices are equal, then that means every element in them is equal. So in this example here, since if we want these two matrices to be equal, then x has to be the same as 1. And y plus 1 has to be the same as 5. 6 is the same as 6, so that works. And then z would have to be 3. So every element has to be equal in order for the matrices to be equal. So that's a simple logical fact that works for matrices. So matrix addition and subtraction. With that, since we're trying to add two matrices, we can only add two matrices if they are the same size. So they all are the same size. And here's some properties that work for them. It doesn't matter what order you add it in. That's the commutative property. We could do A plus B or B plus A and get the same answer. Associative property also works. So these are two properties we know from regular addition that we could, well, group them and add different things first and then add the third item. That's going to give you the same result. And the final two properties are about additive, inverse, and identity. The additive identity property, if we add A, matrix A to a 0 matrix, or a 0 matrix to matrix A, we'll get the same exact matrix. Just like if we add 0 to any real number, it works the same way. And then there's also always going to be an additive inverse. So there'll be, for every matrix A, there'll be an additive inverse, negative A, that will add to it to get 0. So this will work for any matrix. These properties will work. So if we're adding two things, we're going to simply add the different spots of the matrix C. So if I want to add these two matrices A and B, I'm simply going to add each element. So 1 plus negative 1 to get 0. Negative 2 plus 6 to get 4. 3 plus 0 to get 3. And so on. So this is, again, quite logical. You're going to add each element to get your final result. So adding and, of course, subtraction is going to be identical. You're subtracting each element, so it just has to be in the same spot. So pretty straightforward and logical with adding and subtracting. So the 0 matrix is pretty obvious. It's all zeros. And the additive inverse is also pretty obvious. You simply flip the signs of every single term. Because if we want to add to 0, we have to have opposites. So every single term flips to the opposite. So these are all very logical properties of adding and subtracting. It fits with everything we know from before. It's when we get into multiplying that it's a little different. Scalar multiplication, I want you to think of this as kind of distributing. This is when I'm saying I want to do 4 times matrix A. Well, that's simply 4 times this matrix, but that's going to be 4 times every single unit in the matrix. So every single element will get multiplied by 4. and that will give you my result. So that's what this is describing here. If we want to multiply to a scalar, mind you, it's just a single number, c, it's a constant, not a matrix c, and I'm multiplying it by 4, it's simply going to scale everything up by 4. That's why it's called a scalar multiple. And then there's all these properties for scalar multiplication. Once again, they're pretty obvious and very much logical and fit with what we know about multiplication. But know that these lowercase letters, they describe just real numbers. They don't describe matrices. So they're just a single number, not a matrix. So I'm going to skip this example. We'll talk more about that in class when we start practicing it. But matrix multiplication is the one that doesn't fit everything that we know. So when we're dealing with matrix multiplication, we're multiplying two matrices, as you see here, matrix A with matrix B. Here's how it works. When we multiply two matrices, we always multiply row by a column. And that's how we get these two terms here. So we always do the row times the column, and we add the results. And that's what you're seeing down here as well for the first new result. So we do row times column, and that gives me my resultant matrix position. It gives me the next that's in row 1, column 1. And that's how I get this one right here. Now when I want row 1, column 2, I would multiply row 1 times column 2. And then I would add those two products. And that would give me the second part of my matrix. And then again, once I want to find row 2, column 1, I'm going to do row 2 times column 1. And that's how I get the next element in my matrix result. And finally, of course, row 2 times column 2. That will give me row 2, column 2 of my unit. That will give me this result when I perform that operation. So you're not totally distributing, you're multiplying elements C and F, and then you're multiplying elements D and H, like you see here, and adding them together. This is a very unique way of multiplying, but the way this works, it just allows us to do some quick calculations. So they created this method so we could work with things like systems and with ease and with calculated programs and such. So here's the formal definition of matrix multiplication. It will work no matter what. We'll always take a row times the column in the other matrix to get the next value in the resultant matrix. Okay, the one that's in the ith row and the jth column. That will tell me where that resultant element is going to be. So I think the best way to understand this is to see it in action. So let's take a look at an example. So in my matrix, I'm going to start by taking the first row and multiplying it by the first column. This will give me the element in the first row of the first column. So I'm going to do -1 times 4, and I'm going to add it to 2 times -2. -4 plus -4. So I get -8. And that's the unit that will go in the first row in the first column. Okay, now I'm going to do the first row and the second column. And that will tell me the unit that goes in the first row of the new matrix and the second column. So I'm going to do -1 times 2 times 0, excuse me, plus 2 times -3. So I'm going to get -6. So that's my unit that goes here. Continuing on, now I'm going to do the second row and the first column, because I'm on to my second row. And I'm going to do 0 times 4 plus -2 times 1. And it looks like I'll get -2. Second row, first column. Now I'm going to do second row, second column. So 0 times 0 plus -3 times 1. So I'll get -3. Now I'm on to the third row. So I'm on the third row, first column. So it'll be 4 times 3 plus negative 1 times negative 2. And I'll get 12 plus 2, which is 14. So third row, first column, I'm at 14. Now I'm going to do third row, second column. So 3 times 0, negative 1 times negative 3. So I will get 3. Continuing on. Now I'm in my fourth row. Fourth row, 1, 2 times the first column. 4 times 1 plus negative 2 times 2. So I get 4 plus negative 4, 0. And then one more unit for that row. Now I'm doing fourth row, second column, 0 times 1 plus 2 times negative 3. So it'll be negative 6. And I am done with this result. So my matrix is often gonna have a different size to it. Remember the order of the first one here. The order of the first one was a 4 by 2, and we were timesing it by a 2 by 2. What's really important when we do this is that these two values are the same. So the width and the height of the remaining one, because that's how we were able to have enough units to multiply. And the extra values here that aren't necessarily the same will be the dimensions of my resultant matrix. Okay, 4 by 2. So that's kind of an interesting way to allow you to set it up. Because I set my matrix up a little too small, but I should have looked ahead and noticed that this would result in a 4 by 2 matrix. So you're going to try one of these in your checkpoints. And this is what this discusses. So just to clarify, these two values have to be equal, and the result of your product will always be the other two values. So order matters. This is one key thing. Order matters. These are both the same matrices being multiplied, and they get extremely different results. So when we do A times B, we're going to be doing 1 times 4 plus 2 times 5 plus 3 times 6. That's why we get a single value. But here we do row times column, and we get our 4. Row times column, and we get our 8, and so on. And you can continue doing that to get your 12. You would do 4 times 3 to get your 12. And that just creates the first row. So the resulting dimensions are very much related to the original matrices. And certain matrices cannot be multiplied because of the definition of matrix multiplication. So here's your properties. There's not nearly as many. Associative property works, so you can do one pair before the other if they can be multiplied to begin with. And then there is a distributive property, so you can distribute the A, or in other words, or else, even from the back side, if C is on the back, but notice C has to be second here. So order still matters, but you can distribute from either end. And then you can also pull out a scalar, is what this is talking about. The one big property that does not work is commutative. Order matters. A times B is very different than B times A when we're talking about matrices. So here's your checkpoints. Do your best. Bring in your questions. We'll talk about these in class and definitely get more practice with them. And hopefully you're noticing my nice spelling error right here. So bring in your questions in your class on Monday.